let us talk about null graphs. So we have taken null graphs as disconnected graphs, right? So already I told you that this is an exception. That means if you take null graphs as disconnected graphs, you will have some advantages. At the same time, you have some disadvantages. Okay. So sometimes we can't define some concepts. I will show you that concepts where you can't clearly define some concepts. So that's why what I do is in my entire discrete maths classes, so I am avoiding null graph. Okay, so there is no problem if we avoid null graph. That means it will not affect your gate preparation. Okay, so there are two ways, like null graphs can be considered, otherwise we can avoid. But what I felt is if we avoid null graphs, then probably we can understand the concept very clearly. Okay, so but that will not affect your gate preparation. Okay, so yes, null graphs exist, but in the gate exam, whatever the question they mention, so try to answer. If they don't mention anything, then probably you answer with by ignoring null graphs. Okay, so let us avoid null graphs. Then if I avoid null graphs, then you see what happens. Consider this triangle. Okay, now A, B, C, and you know what is vertex connectivity number, right? So let's try to calculate vertex connectivity number K and lambda, where lambda is edge connectivity number. Otherwise, minimum number of edges required to remove from this graph to disconnect this graph. So let's find out first lambda value. So lambda is nothing but minimum number of edges required to disconnect this graph. So we need two edges, isn't it? If I remove these two edges, then probably I can disconnect this graph. That's why lambda value is 2, and k value, minimum number of vertices required to disconnect this graph. Try to remove one vertex, let's say A, then you get this graph BC, right? Then is it disconnected? No. Try to remove B, then there is a single vertex. Still C is connected, right? Single vertex is connected graph, already I told you. Then if I remove C, one more vertex, that means so far you have removed 3 vertices, right? Then if I assume null graph exists, then probably k value will become 3. But we are avoiding null graphs, isn't it? So if I avoid null graphs, then when you remove 3 vertices, you end up with null graph, but we are avoiding null graph. That means we are not considering null graph as a graph. Then, so with that idea, so there is no way of telling that 3 vertices disconnect this graph, right? So forget about null graph now. If there is no null graph, then whatever the number of vertices you delete from this graph cannot be disconnected, right? So we have seen that initially when you removed A, the structure was like this, not connected, not disconnected. After that you removed B, still single vertex is connected. After that you end up with nothing. Okay, so don't say null graph because we are avoiding null graphs. Okay, null graphs makes your discussions complicated, so very complicated. That's why we are avoiding them. Then in this scenario, there is no null graph. Then there is no way of disconnecting this graph by removal of vertices. That's why I say k value. So then what to do? It is undefined here. Further, generally, so how this vertex connectivity number defined is for this kind of, this is called complete graph. For any complete graph it happens. For any complete graph from now onwards, you remember that vertex connectivity number is number of vertices minus 1. Okay, so such a way it is defined, n minus 1, where n is 3 here, 3 minus 1, 2. One more example, let's take complete graph with 4 vertices, 1, 2, 3, 4. For this graph, if vertex connectivity number k is, so we know that whatever the number of vertices you remove, graph cannot be disconnected, right? 1, 2, 3, 4. But after removing all the 4 vertices, you end up with null graph. So, but we are not considering null graph as a graph. Then, so we cannot disconnect this graph, right? So then in this scenario, so k value will become what? Then according to the assumption, it is n minus 1. We have to take it as exception. So it will become n minus 1, where n is 4 here, 4 minus 1, 3. Apart from this, vertex connectivity number can be, apart from complete graphs, so vertex connectivity number is as usual. Example, we'll see a graph which is not complete graph like this. Okay. Always we can disconnect any graph if it is not complete graph. Okay, example 1 2 3 4 5. Let's take lot of edges like this. What about this graph? What is vertex connectivity number? We'll see. Simply remove 2 comma 5, then graph will be disconnected. Then k value is 2. Not a big deal. Okay. So lambda is always defined, not a issue. Okay. From now onwards, you remember I am not considering null graph.